Hello, today we'll be covering the final chapter which is chapter 25 in Physics A Level 9702, titled Astronomy and Cosmology. This is following the updated syllabus in 2022. So we'll learn a few things here, for example, standard candles, stellar radii, Hubble's law, and the Big Bang theory. How did the universe begin? Why do some stars look brighter than the others? How can we find out how far are galaxies away from Earth? Let's start with the first unit here, and I'll also be providing solutions for the questions except for the end chapter. There are a few things you might need to know before this. For example, Doppler's effect, which is a change in observed frequency when a source of wave moves away or towards an observer who is stationary, or when a spectrum of continuous light passes through the cool gas is crossed by a series of darker lines. We will call this the absorption spectrum. The universe is very large. There are lots of stars in the night sky and lots of galaxies and curiosities for us to unpack and unravel. What are the few things we've learned from it? What are the few things that we can deduce from it? Let's start from the basics in this interesting chapter with standard candles. When you, on a clear night sky, if you use a telescope, you notice that you observe hundreds of stars. Sometimes they're brighter than other stars. This could be because they are closer to us compared to another star, or they are brighter. So you can compare this to two lamps. If a lamp is brighter than the other and they're the same distance from us, the brighter lamp will be brighter to us. But if the brighter lamp is moved to a distance so far away, the dimmer lamp comparatively becomes brighter. This is called the luminosity. What is luminosity? Luminosity is the total power an object has, which is the total energy emitted per unit time. For luminosity, our units will be in watts. So let's take a note of this value here, as we will need to use it later. The luminosity of the sun will be 3.9 times 10 to the power of 26. So with reference to what I said about the lamps earlier, what's the apparent brightness? We know that the source, the luminosity of the sun is this value here, but is it as bright when it's further from us, or how can we measure its brightness? Think of it as an area. And this area here will tell us in an equation called the radiant flux intensity, what is the apparent brightness when we are a certain distance away. Because light illuminates this increasing area as it moves out from the star. So the energy is emitted uniformly in all the directions, so it will be spread over a surface area of a sphere, which is why it gives the formula F equals to L over 4 pi d squared. Break this down. Let me write this. 4 pi d squared, where d denotes the distance away from us, will be equivalent to the surface area of a sphere if you consider the radius to be d. So because of this units, area will be expressed in meters squared, which is why using our standard units, you get watt per meter squared. So our official definition for radiant flux intensity, or our textbook definition, to put it into better terms, would be the radiant power per unit area passing normally through the unit area. Let's try a question here. The radiant flux intensity at Earth due to the sun's radiation is 1,400 watts per meter squared. The mean orbital radii about the sun, the Earth, and Mars are 1.5 times 10 to the power of 8 kilometers and 2.3 times 10 to the power of 8 kilometers respectively. How can we find the radiant flux intensity of the sun at Mars? First up, we'll set an equation. Where pi would denote the unit here, as I do not have access to the symbol for the moment. Let's substitute our first values in, where our luminosity is an unknown value. Please remember to convert km to meters as it is the standard unit. And remember to put square too. So this is the value that we are going to use compared to Earth to find out the luminosity of the Sun. We will get a value of 3.96 times 10 to the power of 26. After this, you can substitute this value back on Mars, where your luminosity will be used here, and your d squared will be used in respect to the radii of the Sun, the center of Mars to the center of the Sun. You could also use ratio for this question, although this is a safer alternative where you would not make as much of mistakes. Now, I ideally get an answer of 595 watts per meter squared, or if we follow the significant figures rule, 600. The radiant flux intensity of the Sun at Mars will be 600. So now that we know how bright the source is, or how bright it apparently is from a distance, we want to find out what's the distance of stars and galaxies away from Earth. We know that a galaxy has hundreds of millions of stars, dark matter, stellar remnants, gas, remnants like the asteroid belt or fragments of planets that collide with asteroids, and of course a black hole at the center. So they're held together by strong forces of gravity. So how do we determine how far this object is away from Earth? We will use standard candles. So what are standard candles? Standard candles are essentially a bunch of stellar objects where we already know our known luminosity, and we also know its radiant flux intensity. So by plugging this value back in, we will have to rearrange d squared to find out what is the distance away from Earth, the basic one. After rearrangement, you should get d is equal to root of L over 4 pi f. Now, we have an issue here. How are we going to determine the luminosity in the first place? There's a way to overcome this problem. We use something called Cepheid variables, where its radius varies periodically. So it causes the temperature of the star to change and the luminosity always varies. Scientist Henrietta Swan Leavitt in 1908 discovered that the more luminous Cepheids have longer periods, and there's a relationship between the period and the star's variation in luminosity. So if you plot a log graph here, please be careful when measuring units. And this is with respect to the luminosity of the Sun, which had a safe value of 3.9 times 10 to the power of 26 watts. You can draw roughly a straight line graph to find the distance to the star after measuring your radiant flux intensity. Let's put this example into practice, closely referring to the figure 25.3. For example, if a Cepheid variable has a period of 10 days and its radiant flux intensity is measured as 1.4 times 10 to the power negative 10 watts per meter squared, how can we estimate its luminosity? So, looking at this graph, if we have 10 days, it's a bit difficult to determine here, but if we unlock the graph from here and we multiply by the units, by the luminosity of the Sun, we can get a rough estimate of 5.5 times 10 to the power of 9. So by plugging the earlier equation, F equals to L over 4 pi d squared, we can rearrange our value of d as such. L over 4 pi f, where we know its radiant flux intensity and luminosity, will give us an answer of, following the significant figures rule, 1.8 times 10 to the power of 19 meters away. which is an extremely far distance, mind you. There are also other standard candles, but they don't really work for Cepheid variables if they are really far from Earth. So you cannot use other standard candles such as supernovae, which are stars that have exploded as its lifetime has ended. We could also use that to measure the distance for very distant galaxies. So let's take a look at stuff like stellar radii. Suppose you have a steel ball. It's roughly grayish, silver in color, let's say. And if you hit it really strongly, it goes from red and it keeps on increases to bright red. So it's actually radiating energy here. And this brightness will go depends on what's the rate that the radiation is emitted, which is the intensity. And it also depends on what's the intensity of the wavelength of the emitted radiation. So we have an idea of a black body. For example, if the sun did not radiate any heat, it would theoretically look like a black body. But because it's emitting so much heat, it looks red in comparison. Scientist or astronomer William Wynne discovered this relationship between what's the maximum lambda and the temperature at which it occurs, which is known as Wynne's displacement law, which also pretty much explains why our sun looks pretty red in color in comparison. But as your temperature increases, the blue stars are actually commonly known to be hotter than our sun's temperature. This is actually a fun fact as when I was at a when I was younger, I thought that red stars actually emit more heat than the blue stars, but it wasn't so apparently. There's a relationship to be followed, which goes lambda max will be equal to E over T. Normally in the exam, you're not required to know of this knowledge or memorize the Wind's displacement constant, but it would help to know that this is the value 2.898 times 10 to the power negative 3 meter Kelvin. Let's head over to next question, question 3. So we have two stars in Orion, a constellation called Rigel and Betelgeuse. Their wavelengths of peak intensities from each one is 240 nanometers and 878 nanometers respectively. Let's rearrange the equation to make it a little easier for us to calculate the thermodynamic temperature. After rearranging it, we'll notice that T will be equal to Wind's displacement constant over lambda. So taking note that nanometer is equal to 10 to the power negative 9, you should get for the Rigel, I'm sorry if I mispronounced this, as 12,100 Kelvin. Always take these values of thermodynamic temperature in Kelvin. And it is an SI unit. And Betelgeuse, I'm very sorry if I pronounced this wrongly, 3,300 Kelvin. Now that we know these values, and now that we know what's the luminosity of the star, how we determine it, two scientists, Joseph Stephan and Boltzmann, discovered a law where luminosity increases as your temperature rises. But what exactly is the observation here? It was discovered that it was proportional to e to the power of 4. And also its area, as you can see, 4 pi r squared. So this is our constant that is provided in page 2 or 3 of the booklet in the physics exam paper. So you need not be worried about that. So it states that our Stefan-Boltzmann law is equal to 4 pi sigma r squared T to the power of 4. Formula is also provided on, I think, the third page. So you do not need to be worried about memorizing this. So this is how we can find stellar radii when we found the luminosity and also an intensity maximum, in which this intensity maximum will be able to lead us to meaning the thermodynamic temperature because of Wind's displacement law. So let's try an example. The ray giant star Aldebaran has a luminosity of 1.95 times 10 to the power 29 watts. So our wavelength corresponding to this peak intensity is 725 nanometers. So what is the radius? It sounds a little scary at first, but let's do a little rearrangement so that we can figure out our answer quickly. So R equals to L over 4 sigma T to power. So how do we find our temperature? It isn't stated or anything. Remembering Wien's displacement law, we can find our thermodynamic temperature by T equals to B over lambda. So plug in the values of 2.89 times 10 to the power negative 3 and 725 times the power times 10 to the power negative 9. Raise it to the power of 4, multiply by the Stefan Boltzmann constant, and the luminosity is divided by our answer. And after performing a square root, and of course, converting it to kilometers as our answer was in meters, you should get following the rule 3.3 times 10 to the power of 7 kilometers. So these are an introduction to some of the equations that we might be using, and I am willing to learn more about this field in the future. And the thing that fascinates me the most is Hubble's law and our Big Bang theory, how galaxies have been expanding, how we can determine how fast it's moving away from Earth, how far it is away from Earth, and the age of the universe. We know that galaxies have trillions and trillions of stars, around 10 to the power of 11 on average. And there are so many galaxies in the universe that we can't even count them. So how do we know more about galaxies and how far is it away from us and how fast is it moving away from us? We'll go back to our law as the Doppler's redshift. As you can remember from Doppler's effect, if a person is stationary and a sound source moves towards or away from the person, the frequency varies. So applying this law, we can actually do the recorded absorption spectra in a distant star and compare it to a star that's near or usually determined in a laboratory. So how can we exactly work this out? And what exactly is blue shift or redshift? So we know that redshift is an increase in the wavelength, which gives the hint that this star is moving away from us, while blue shift means that this star is moving towards us. How can we measure Doppler's redshift rule from here? So we know that our apparent wavelength is c plus a certain speed towards the observer or away, divided by the frequency from the star. So since the frequency is also equal to the speed of light divided by lambda from the stationary source, we can determine that at the end, the change of lambda over our laboratory or experimental value is also equal to speed it is moving towards or away from us over the speed of light. So let's try an example for question 5, where measurements of the spectrum of light from the galaxy NGC 4889 indicate a wavelength of 401.8 nanometers for the wavelength of this K line of singly ionized calcium, but the value measured in the laboratory was 393.3. So how do we calculate the change in wavelength? You always use the final minus the initial. So 401.8 minus 393.3 over 393.3. And you can actually exclude the values of nanometers here, as these two cancel each other out to 10 to the power of 9, which is also equal to the v over the speed of light, which is given as 3.0 times 10 to the power of 8 meters per second. Now, if your answer needs to be expressed in kilometers, don't forget to divide by 10 to the power of 3. As your answer in standard units will be obtained in terms of meters. You should get roughly 6,500 kilometers per second away from Earth, which sounds like a pretty fast rate, as it can circumnavigate the Earth every, say, 7 seconds. Now, we've come to the most interesting part from an astronomer, Edwin Hubble. So he calculated redshifted galaxies and found that they were moving away from the Earth. And using the standard candles methods, he determined the distance away from the Earth and how far are they moving away from Earth. So using the Doppler's redshift, we can make a general assumption or conclusion that the further away the galaxy is away from Earth, the faster it moves away from Earth. Of course, we will compare it to where we call home. So as there's a scatter of lines here, a line of best fit is usually drawn. So we know that V is proportional to D, as radius V is proportional to distance, and our constant will be called the Hubble's law. Now, here's an issue with Hubble's law. We don't know the exact value since the points are so scattered around. So with more experiments and testing, our Hubble's law is becoming more precise, but not exactly there yet. So our Hubble's law is currently accepted as not really 75 kilometers per second per megaparsec. It's actually closer to 70. But of course, it depends on what value is used. But from the latest news that I read, it was stated at 70, closer to 70. So by using this equation, V equals to the Hubble's constant times the distance of the galaxy away from Earth. Let's try question 6. So NGC 489 has the using the redshift 6,500 kilometers per second from Earth. Is moving away from Earth, which is the answer that we got earlier on. So let's assume that Hubble's law has this constant, as it isn't clearly defined or hasn't been clearly determined yet. How long does it take for light to travel from this galaxy to Earth? It sounds pretty scary, but always remember, let's convert 6,500 to SI units. Equal to the Hubble's distance. Times the distance. So we can find out our distance is 2.71 times 10 to the power of 24 meters away from Earth. So how long does it take to travel to Earth? Because it says for light to travel. So light is at 3.0 times 10 to the power of 8 meters per second. So what we do here is divide this, and we shall get our answer in seconds of 9.03 times 10 to the power of 15 seconds. Now we have to express this in years. So you have to divide by 60, then by 60, then by 24, then by 365 to get years, which will be equal to 2.9 times 10 to the power of 8 years. I think that takes about 290 million years, which means that if we were to observe NGC 4889 today, we will actually be viewing the galaxy from 290 million years ago. It seems like an extremely long time for us human civilization, but for space, it's barely a stretch of time. This is a much smaller topic, but we also have quasars in the universe, which are very distant objects, very large redshifts, and a very huge luminosity, which is over 10 to the power 14 times more luminous than the sun. So these quasars can help us enable the study of objects which are really, really far from Earth, as Cephei variables become harder and does not really apply to galaxies and stars that are further away from Earth. So we have a cosmological principle from Albert Einstein, where we know that the time taken is equal to V. But we know V is also equal to the Hubble's constant times the distance. So if the galaxy is further away from an object, it moves at a at a faster rate. But if it's closer to the object, it moves at a slower rate. So the theory is that everything was at one point together, so they had zero speed. So how do we find this value here? We know that v is equal to h over x, and speed is also equal to x over t. So if you notice, these values can cancel each other out, and we actually get our age of the universe to be 1 over the Hubble's constant. As the Hubble's constant isn't exactly so sure, our best estimates for the moment is that the universe is about 13.8 billion years old. This is our best estimates. 11 billion to 20 billion years is a pretty large stretch. And 13 billion years is pretty close, although we have gotten a value closer to 70 instead of 75 kilometers per second per megaparsec. Let's try our final question for this check. Question 8. So, the distance between the moon and the earth is approximately 3.8 times 10 to the power 5 kilometers. That sounds like a very short distance in the space, because it is. And so we need to calculate a value for a change in distance between the moon and the earth as a result of the expansion of the universe. So a little fun fact about the expansion and the moon moving away from the earth, there will come a point where the moon is unable to perform the solar eclipse anymore because it's so far away from the earth that we create like this ring instead. So because the moon and the earth also have gravitational forces together, the moon also controls the tides. So if it moves further away from earth, slowly but surely, there will be some consequences and effects on earth too. But the value is so insignificant that we may barely notice a thing in our lifetime. So enough rambling from this part. Let's calculate this value of how far is it from Earth. So we know that v equals 3 Hubble's constant and it's x. So Hubble's constant h0 here, but it's actually a subscript. So please take note. So we know that x over t, because it's our speed. Oh, sorry. We know that v is also equal to the value that they gave us and multiplied by the distance. And please convert to meters as it is in standard units. In the end, we'll get our v, which is equal to 9.12 times 10 to the power of negative 10 meters per second. So they want to ask, how far is the moon moving away from Earth per year? So you will need to multiply this by 60 and by 60 and by 24 and by 365. So we will get our value of roughly, let me write it down, 2.88 times 10 to the power of negative 2 meters traveled in 1 year. Converting into centimeters, so it's a little easier. So following the significant rule and following this Hubble's constant, the moon is moving away from Earth and approximately 2.9, about 3 centimeters away from Earth per year. So in my lifetime, the moon would have only moved away from Earth equivalent to probably half the length of the room I'm in. So it's very insignificant, but over tens and thousands and hundreds of thousands of years, it will eventually be so significant that it impacts the Earth's tidal waves and many similar things like this. Let's do a little summary as we might not have enough time for end of topic questions. For Wien's displacement law, please do not be worried as you do not exactly need to memorize it, although it's recommended, and things like Stefan-Boltzmann law will be provided, but radiance flux intensity will not be provided, so you will need to memorize this. So what is luminosity? It's basically how bright an object is. What's the power radiation that the object emits? Like for example, the light, which is usually say 10 watts, 13 watts. I'm being generous here. And what's the radiance flux intensity? Radiant flux intensity. It means the apparent brightness. What's the intensity per unit area and for the area to be normal to the luminosity, the intensity. So if we know the luminosity and the radiant flux intensity, we refer to them as standard candles, and we can rearrange the formula to determine how far it is from Earth. And we can also use Wien's displacement law to find the temperature of things like, for example, how do we know the temperature of the sun? Next, we also know Stefan-Boltzmann law, which is proportional to temperature to the power of 4, and also the surface area of a sphere. So we know that our constant is a given value, which does not need to be memorized. So it relates luminosity to the temperature. And also, if your radius increases, your luminosity increases too. And you can combine Wien's displacement law with the Stefan-Boltzmann law because you do not immediately know the temperature, you only know the wavelength. And you can also determine how far a galaxy is moving away from Earth, how fast it's moving away from Earth, and how far it is from Earth using our Doppler's redshift formula. Of course, if it's moving towards Earth, it will be blue shifted, so a change in lambda will be negative. So always use lambda final minus initial. And because of Doppler's redshift, it leads to the concept that the universe is expanding. Everything is moving away from each other. So if we use our Hubble's law in our theory, we can theorize that everything started at a single point and just kind of exploded. So using 1 over Hubble's constant, we can find out how old the universe actually is. And as far as we know, the furthest we've ever seen in the universe is about 13 to 14 billion light years away. And because it takes 13 to 14 billion years for the light to travel here, what we're essentially looking at is actually the formation of the early universe, which a picture is available on Google. So, fun fact, if let's say we have a galaxy which is 65 million light years away from Earth, they would still be able to observe the dinosaurs in our solar system on Earth, of course. And there are a lot of interesting things about astronomy and cosmology, and that I'm interested in exploring more. And I hope this video has helped you in an introduction to this topic. And as always, if you have any inquiries, just email me at chrisbloggerhg@gmail.com. You can also write to the same email if there are any copyright issues. I'll be referencing this textbook in the comment section. Thank you for watching this video. I hope it helped.